searching for the export get proc address itself within the PE manually. We're going to do that manually. Essentially, we're going to do what get proc address does, basically, not exactly perhaps in the same way, but the same kind of idea. But we're going to do that manually by looking at the PE itself, by looking at kernel32.dll, which is where this function is being exported from. Okay, so that's going to be our next step, which is probably the most complex part, or one of the complex parts here. So I want to call this function, I want to create this function called find export. I want to return the address of that function, whatever that address may be, some void pointer. And then I need to have the DLL name. That's going to be kernel32, but we can generalize this function to work with any DLL really. And then we need the function name, which is a normal C string. So it's going to be perhaps get proc address, but in fact it could work for any kind of function. And I'm going to also return, while I'm at it, the handle to the module. I'm going to return that so that we can use that. I don't want to call get module handle, because that would make get module handle a function, which again is going to be visible in the export table. I want to keep it very similar to DarkSide, so that we only have the exit process there within the import table. So how do we do that? How can we find the export? So there are two steps here. The first one is to find the DLL itself. And the second step is to parse that DLL as a PE, as a portable executable, and find the export section, all that stuff, and get to the address of the exported function. So the first step is to find the DLL that is loaded into our process. And the question is how we're going to do that. And the answer is that the list of DLLs in our process is stored in the process environment block, one of these semi-documented structures that we can use. And so we can, in fact, get what we need using another header file, which Microsoft reluctantly is providing to us, called internal.h. And with internal.h, we have some internal structures, not fully documented, but good enough for what we're trying to do here. So for example, the PEB structure here, if I look for it, here's the PEB structure. You can see that most of it has this reserved stuff, indicating that Microsoft doesn't want to expose what these fields are. Of course, we know what these fields are because they're available in other sources, but officially Microsoft is not keen on exposing these internal structures. However, all we need here from this structure is this location, this member called LDR, which is of type PPB LDR data, which is pointed to this kind of structure. And this structure has a bunch of list entries. These represent a linked list. This is a dynamically linked list that stores the list of all the modules, that is all the DLLs in the process. So if we walk over this list correctly, this list entry just points forward and backwards to the next entry and to the previous entry. If we walk correctly over this list, we'll be able to search for the DLL in question. Once we find this entry, it's going to point to this kind of thing. And this entry has finally the DLL name we can compare to, the full DLL name here. And it also provides DLL base. That is the address where this DLL is loaded into memory. And remember, these addresses are not fixed. So every time you restart Windows, it's going to be a different address for these DLLs. This is based on a feature called ASLR, or Address Space Load Randomization, which was available since Vista. So to make it harder for shellcode to execute, these addresses are generated pseudo-randomly every time we restart Windows. So we don't know the address up front. We have to figure it out dynamically ourselves. But once we get to this structure, we have the DLL base provided to us directly, and we can then move to the second step, which is to parse the PE. So let's see how we can do that. The first question, of course, how do we get a pointer to the PEB? So fortunately, there are in fact a couple of ways of doing that, but the simplest way to get it is using the startup function. In fact, the startup function actually is providing us with a PEB. This is perhaps a little known secret, but in fact, the main CRT startup, whatever function we want to call for that entry point, actually is given the PEB by Windows, by NTDLL that calls this function. So we actually have the PEB already in place. So I'm going to grab the PEB here and pass it to this function as well. So what we want to do here in terms of the call, I want to get to this get proc address function. So I want to say get proc address. I want to call find export, not executable, but export. I want to give the PB, which is necessary. The full DLL name is kernel32.dll, what actually just the file name. I don't really want to deal with the actual directory it's stored in, because it could be, in theory, different in different versions of Windows, different installations. And then the function name is getProcAddress. And I also want to get back this hkernel32 here, which I'm going to now specify here. And this is going to be used later on to call the other style function. So now instead of calling getProcAddress like so, I'm going to use pgetProcAddress, so that getProcAddress, I'm going to get that dynamically. Once I have that dynamically, then I'll be able to just call it kind of normally. So of course we have to, as usual, cast it so the compiler is happy to the actual type. And we can get that type by getting some help from C++ using decal type. So the only thing remaining here is to find the export. I mean, how difficult can that be? So let's first get to the head of the list. So one thing to note about this list entry thing is they're managing a circular linked list. So we don't iterate by searching for a null pointer. That's not going to happen ever. Instead, we need to look for the head. So we need to iterate, and once we get back to the head, it means that we're done. So we have this PB pointer here, and we have there the member called LDR, and there we have the in-memory module list. That is the actual head. So I'm going to stash this head pointer here in my local variable. Then I can start doing the iteration. So I'm going to start with the first item, with head f-link, the forward link. I want to move as long as next is not the same as head. So as long as I haven't made the full circle, because if I made a full circle and search for some DLL and it wasn't found, then it just means that the DLL name doesn't exist in the process, not loaded into this process, and that's just an error. By the way, this symbol, don't worry, it's a normal C symbol of not. I'm just using a font called Cascadia Code that has these nice ligatures, so it combines some of these symbols to make them nicer to view. So don't worry, the C language hasn't changed while you were sleeping or something. And then we're going to just move to the next one by going to the forward link. So here we need to grab the actual structure of this type that I mentioned earlier. Let's go here back to see what's going on here. So we have this LDR. We need to grab this data structure, which is actually being pointed to by the list entries that we start iterating from here. Again, I'm doing all these things pretty fast simply because we have limited time here, but just know that this is going to be explained in a lot more detail and rigor when we do the full workshop, of course. So we have here this entry here, and we need to actually cast this thing. This is going to point to the inner list entries here. We need to point back to the beginning of the structure. This requires some changing of offsets, and fortunately there's a macro that is provided to do that for us. So we're going to take the entry here. We're going to use the containing record macro. So this macro takes the existing address, which is next, the type that we expect to get, which is LDR data table entry. So let's grab that. And the name of the field is in memory order links. That's the name of the field of type list entry within that data structure. Again, the rationale here is perhaps requires more explanation, but for now, I'm just going to do that because that's what I can do in this case. So when we look at this entry, you can see here, entry, if I write this correctly, you'll find that we have here what we're looking for. We have the full DLL name and the DLL base. We just need to locate the correct DLL name. As you can see here, the full DLL name has a type called Unicode string, which is the most common type of string used within the kernel and by anti-DLL APIs. And since this is coming from anti-DLL, the PAB stuff, then we have Unicode string here, which is just a string that has a pointer to the set of characters and a length. And essentially, it is not necessarily null terminated, which means we have to do some searching there, which is not going to be very fun, perhaps, but it has to be done. So here's how I'm going to go about it. I'm going to have to search manually. And the reason is that I don't want to have another function be used. There is, in fact, a function in the native API that will help us search these, compare these strings, but it's not going to be good because it's going to end up in the import table, which I want to prevent. I want to do everything manually. So I have to compare strings manually as well. So I'm going to take the entry here. I'm going to take the full DLL name. And we have the buffer where the characters start. I'm going to go to the last one and then work my way backwards for searching purposes. So we have here again entry, full DLL name, and then length. And the length is actually in bytes, not in Unicode characters. That is not in UTF-16 characters. So I have to divide by the size of a UTF-16 character, which is 2 bytes. I'm going to actually have here a pointer pointing to the past the last one character. And then I'm going to also need to calculate the length of the string that I get, which is the DLL name I'm getting from the parameters here, because I need to search properly in terms of length. Now, the problem again here is that WCSLen is a function from the C runtime, which I no longer depend on, so I can't really call that. So I have to write my own WCSLen. Not too bad in this case, but we'll have to do that. So as you can see, there is some more work involved. I'm going to call that with a different name, just so it's easier to realize that this is not the original C runtime function, but this is something that I've written here because there's just nothing else I can do. And so while we have this pointer, the referencing that is not null, we're just going to add one to len. We're going to return len. That's going to be the length of the string. So in this case, it's fairly easy to do. But again, these things could be found online. These are just fairly simple functions for doing the length of the string. So now we need to actually perform the comparison. So I'm going to use the while loop here, and we're going to move backwards and look until while we have the same characters in both of these. So we have DLL name here, and we're going to use the index I here again. I points to the end of the string, really. Points in terms of its length. So while this is true, we just need to do nothing. If it's false, then it means something is wrong. So if the last character at this point is a backslash, remember that what we have in full name is something that includes the full name of the DLL. It's not just the short name. So if we have a backslash here, it means that the string actually matches and we're good to go. So we found our DLL. Now we can say grab some base address and do something with it. So in this case, let's just have a simple, the base address, let's just write here like so. Base address is going to be what we get from the entry, which is going to be the DLL base. That's the address where the DLL is being mapped into memory. And this is the address we're going to use to parse the PE. Now, this is not exactly right because the comparison here is case sensitive, which is not very convenient. So we might want to make it insensitive because I might be passing this kernel 32 here, perhaps with a certain case, and I don't want to miss the comparison based on case. And so doing this comparison is case sensitive, which is not what I want. So again, I can't call some function like toLower or something to convert that to lowercase, for instance. I'll have to do that manually. So I need to go ahead and end this with not 20. So why is that? It seems pretty arbitrary. So if you think about how casing works in ASCII, if you have the capital A letter, for example, that's 41 hex, and the lowercase a is 61 hex. There's a difference of 20 hex, which is just bit 5 being lit up. So I want to turn off that bit. And this is how to turn a bit off. In this case, I want to turn bit 5 off, which has the value of 32 or 20 hex. Again, all these things are going to be explained in more detail in the full workshop. And I'm going to do the same thing here. So I want to just basically convert these to lowercase for comparison purposes. So let's try this before we actually continue. Let's try to see if it actually works. So I'm going to put a breakpoint here. In fact, let me put a breakpoint here before that. So we'll see what is happening when I'm trying to debug this thing. So find export has to return some value here, of course, but for now we'll just return null. So let's run this by pressing F5. It's going to build and run. So we're running with a debugger now. And we get to this location here. So we have the head. So the head is just some pointer. It's not really very interesting at this point. Now we move to the first entry, and this is the entry. So notice the entry here has these values. So notice the DLL base is this one. This is just some address, but more importantly, the full DLL name is here. So you can see it, in fact, the executable itself. You can see it is the executable itself because that's the first module that is mapped to the process. So you can see darkside2.exe. This is my module right here. So that, of course, is not going to work out in terms of comparison. We have to move to the next one. Moving to the next one, let me even use maybe entry here to make it easier to see, perhaps. So we can see that now the next module in line, it's supposed to be anti-DLL. Let's just verify. So the full DLL name here is indeed anti-DLL, which is always the second thing that is being mapped into a process. So obviously, that's not the right one. So this is not going to work out. It's going to fail the comparison. And the third one might be kernel 32. Let's see. So here's our entry. And in this case, it is in fact kernel 32. So we expect this breakpoint now to hit. So let's go and we see that it actually hits. And this is the address. This is the handle to the module for kernel 32 in our process, which means now we can move to the next stage to look for the export in question, which is this func name. In this case, get proc address, but could be any function really. And the DLL name also could be any DLL name. So as you can see here, in order to avoid the detection, avoid being noisy, we have to do things manually, such as parsing stuff like the PEB, and as we'll see, parsing the PE as well, and doing things like calculating the length of a string just because we have to do that. So the next step is to actually find the function address itself. So let's create another function called getFunctionAddress. And in this case, we need the base of the DLL, and we need the name of the function. So essentially what we're going to do here, once we have this base provided, we can call this function getFunctionAddress. We can provide the base, which we have worked hard to find. And then we need to also provide the name here. So the name, of course, is func name that we get from the function itself. And we also want to cast this to base. So we want to return that handle back to in fact, to the caller. So we want to just, it's not a handle, it's H module, my bad. And if we go over all the entire loop and we get to the end, it means that we're in a position where the DLL was not found. So for example, if I go ahead and look for something else, say the user 32 DLL, which is not supposed to be loaded into my process. So again, we have the case that we have to return something here for the compiler to be happy, so we can do that. And if you run this, we should end up in a case of failure. So if I run this, we can see we end in a case of failure where we have we didn't find the DLL in question because it is not in our process really. In fact, we can have the window here for modules, and you can see that in fact we have only these 4 modules within our process. We don't have user32.dll. Okay, so the next step, let me just bring back here kernel 32 so we don't get things messed up. The next step is to parse the PE. Since this is quite elaborate code and we're kind of running out of time a little bit, so I'm going to do some copy pasting from code I've written before. So it looks something like this. Let me just copy paste it here so we can make forward progress easier. So here's how to parse a PE. Parsing a PE, of course, is a well-known thing, but it has some intricacies. It's not necessarily trivial, but here's the gist of it to get to the exports. So first thing, we get the base of the address, which is this structure called image.dos header. These structures, by the way, are provided by Windows. So you can see here it's in a file called winnt.h, which is a very fundamental header file that is used in Windows for user mode and kernel mode code. So we just know that this always starts with this header, and then we have this member that's pointing to the real header called image entity headers 64 in this case, because I'm building a 64-bit application. There's also a 32 variant, which works in exactly the same way. And then we need to go to this thing called optional header, which is not really optional for images. It has to exist. And there's this bunch of directories called data directories. You can see that here. Let me go to something like kernel 32. This is what we want to actually see. Here are the bunch of exports here. And you can see there's these data directories, and one of them is the export directory. So this export directory has information about all the exports. And what we want to do, we want to get to a get proc address, that particular export we want. We need to find this information, such as the function RVA and name RVA. RVA is short for relative virtual address, which is basically the offset from the beginning of the file, so to speak. And once we have that, then we can bind to that function. We know where it is in memory, and we can finally return that to the caller. This is what we want to do. We want to perform this kind of parsing, which is done by certain tools like this total PE tool. So now we have to do that manually. It's not too bad, especially once you understand how PE files work, then it's not too bad. Of course, we'll deal with PEs in more detail in our full workshop. So we need the particular entry in the data directory for exports. So there's an index for that, it's actually 0. And then we need to get the actual structure there when we move forward to where this is stored in the PE using the virtual address offset. Virtual address is not really an address. Again, this is misleading. This is an RVA. So it's actually an offset from the beginning of the file. So this is the beginning of the file. And now we need to search for these names like manually. And so the way to do that is to find where the names start. So we have the count of names. We have the offset where the names are stored, and this is where the names are actually in memory. And this is the location where the addresses of this function are. So we have these two tables. You can think of that in this way. We have one table for names, another table for addresses. We need to locate the correct name and then take the corresponding address. That's what we want to do. Now, technically, the way the real getproc address works is that it uses a binary search because the export have to be always sorted in alphabetical order. So it makes the search faster. But I'm going to use a different approach, a simpler one, just searching linearly. It's not too bad, and it's not that important for the purpose of this demonstration. So we need to first go ahead and compare two strings. Again, we can't call C runtime functions because we don't want to have any kind of dependency of that. So I added this function myself called equal strings that returns a Boolean indicating whether two strings are equal or not. So I'm going to, again, paste it from existing code. It's just doing comparison of two null-terminated strings. Again, the code is not very complex, and if you're familiar with C, it should make sense. So now we have to check the name. Do we have the correct name? If we do, then we're done. We're going to take the address based on the index and add that to the base of the image. And that is it. This is what we want to return to the caller. If the name is not correct, it's not the right name because there are many exports there, we need to move to the next export. And the way to do that is to move by moving to the next string because they are null terminated. And so we need to know the length of a string. So again, we don't have that kind of function. We have something like this, WCS len2 for Unicode strings. And to get something for ASCII strings, it's also fairly straightforward. So I'm just going to do this little change here for ASCII strings, and we have this strlen2 function working for us. Now, there's another slight complexity, unfortunately. Some of these exports here are not really true exports, but in fact are forwarders. These forwarders forward the implementation to a different DLL. And so they're not true exports, and we have to skip them. You can see here, this is an example of forwarder. Get package full name is exposed using kernel 32, but it's actually implemented in kernel base. The reason that it's exposed in kernel 32 is because of compatibility concerns. And that's actually used quite a lot. Even when you just start out, you can see there are two functions here. There are actually forwarders to functions within NTDL. So we have to skip those. And that's what this check is all about. If the address is within the export table itself, it means these are just forwarders. We need to skip to the next item in line. So to see that in action a little bit, let's go ahead and run this again. Looking for get proc address in this case. This is what we want to get to. Otherwise, with that we can do anything we want. And we found the kernel 32 DLL, but now we have to parse the actual piece. So I'm going to move to this breakpoint. And so names, if I look at some memory here, let me type names. you notice that we have here the names of the functions all separated by a null terminator. So we just need to look for the function in question until we find it. So here goes. Let me put a breakpoint here when we find the function name, hopefully. And here goes, we found it. The I index here is 696. And the name indeed is getProcAddress. Going back to kernel 32, looking for getProcAddress here, let's find it. You can see the ordinal is exactly 696. Okay, so this is the correct one. We found the correct entry, just like any other P parser will do. In fact, this is how getProcAddress works behind the scenes if I wouldn't need to write it, which I'm doing right now. And so we have the address at index I here. And so address I, if I look at what that actually is, you can see this value here. Let me change that to hex, is 1B1D0, and it should be very similar to what we see here. You can see 1B1D0. In fact, it has to be, of course, the same. So this is where the function starts from the beginning of the address the image is loaded into. So we're using that to return that to the caller. So once we have that in place, we're going to go back. Now we have the pointer to getProcAddress. Notice that the debugger, since it has access to symbols, sees all that stuff and indeed gives me an indication this is the correct function. And now we can get create file dynamically here and read file dynamically here. And we can do exactly the same thing with all other functions that we need. So what we've done here, just to summarize this little piece, we looked for the function getProcAddress. Without getProcAddress, we can then get all the other functions just by calling the getProcAddress function, but we don't want getProcAddress to be visible in the PE, and now it is not. So if I go back to looking at my dark side executable here, looking at the imports, we can see getProcAddress is not here. It's not here anymore. And of course, there are some other functions which are left here, which we're going to very quickly turn into just global pointers, just like we did with these couple of functions right here. So that's the basic idea, to locate getProcAddress by parsing the PE. I hope it's not too fast. So the other part, I'm going to do some copy pasting here because we're a bit short on time here, is to try to create some code within a separate section. Normally, you can see here, if I go back to the PE, we have a bunch of sections here, and the code is typically stored here in the text section. Now, what DarkSide does, it stores its main code within text1, a different section, and then uses the small code in the text section to actually decrypt that thing. So can we do something like this? And the answer is, of course, we can do that. We can do that as well. So here's an idea of how we can do that. So first, let's say I have this function. So it really depends on what I want to put inside a separate section, but this is very easy to do in Visual Studio. So for example, if I want to put my function that encrypts a file into a separate code segment, I can use the pragma here called codeseg. I can give it some name, like .text1, to mimic what DarkSide is doing. And now every implementation stored here is going to end up in that section. So let me close this section here, just for demonstration purposes. So we're going to do codeseg without any parameters. And once I do that and rebuild this, you'll notice that now if I open up DarkSide again, well, my DarkSide, you can see that now there's text, but there's also text1. So some of the code now is within text1. And so to put code in a different section is fairly easy. The tricky part, of course, is to encrypt it. To encrypt it so it's not visible anymore. So how do we do that? We do that offline with an offline application, a different application. We can't do that while this DarkSide itself is running. It's too late. We need to make sure this is encrypted when we look at this code through static tools. So we need to add another project to this solution. I'm going to do some copy pasting here to make it faster. So I can call that encdeck section. So I want to be able to encrypt or decrypt any section that I want in any binary that I want. So I'm going to, again, do some copy pasting here to show you how that is done. And describe the code instead of typing it manually, because it's just going to take too much time. So here's the idea. I have a simple application. Of course, it's not something I'm going to publish anywhere as someone that is writing, say, malware. This is just my own little tool, so I can call any function that I want and not really care about using the standard, the C runtime library or any other APIs. Nobody needs to know. So what I want is to be able to take a section and give it an image path, that is a DLL name or an executable name, and a section to encrypt, and just use some kind of encryption, which is using some kind of code here, which of course we can choose anything we want. This is just a XOR encryption. We can do anything. So what do we need to do here? We need to first open the file. So I'm going to call create file to open a handle to this file. Then I want to map it into memory to make it easier to work with. So I'm going to use the create file mapping API to open a file mapping object onto this file, and then map it to memory. And again, I need to find this section, this time using the same kind of ideas as parsing the P that we've done previously, but now the file is just open as a data file. It's not really loaded as an image, it's just open as a data file. So I need to grab the parsing of the headers, but this time I need to look for sections. And the section headers, which is a structure that describes sections, is right after the headers. So I need to find the correct section name by comparing the strings, and we're going to use the simple str compare here. So the section name is going to pass here as argv2. Once I find the section, I'm going to encrypt it using the particular key. And so the way to do that is to simply run over this memory and do the encryption. Once I do that, we'll see the section being encrypted. Just to prove that, let's open our dark side at this point in time. Let's first build this to make sure everything works as expected. Let's open dark side here, say in IDA. So I'm going to grab my executable and put that into IDA. So it's a new file, fine. It will do something, and unfortunately it puts it in my other screen. So here goes. So you can see some functions here, and we have all the functions that we've written. But of course, I have a few functions that I haven't yet removed completely using the pget proc address, but it's not really the point here. The point here is that there's this function encrypt file, and encrypt file is the function that's encrypting the file, and it is part of the text1 section. If I press tab here, then IDA is able to provide a C-style code to show the code that I actually written before. By the way, the reason that we have all these function names exactly as I've written and so on is because IDA here has access to debug symbols, the PDB file that I've generated with Visual Studio. Normally, of course, I wouldn't have that for a malware, but for debugging purposes, this is very useful. At the end of the day, eventually it won't look like that. Anyway, let's close that. So I'm going to close it and not to save that. And I'm going to now perform the encryption for text1. So I'm going to call encdec section, my new application there. I need to take darkside 2 and use the text1 section for encryption purposes. So this is done. And you might notice even in total PE that the code looks different here. Let me verify that. So here's the text1. It looks different than it did before. But more importantly, let's look at that from IDA's perspective. So let's open this recent file here and try to look at that again.
Pavel, we need to finalize.
Yes, I'm going to finalize momentarily. And you can see here the enc function. So that's the function I was looking for. And that function is no longer showing correctly. So in fact, what's going to happen here, let me just close it and make sure that IDA is properly refreshed here. And we should see the enc file function here somewhere, but it's actually going to be garbage. There's nothing the IDA disassembler can actually show us. We won't be able to see anything here. It's just junk code. And so at runtime, we can call an encryption decryption function to actually make text1 again visible and just use it. And so because we're running out of time, I'm going to post a recording of these last stages and all the stages, in fact, that I've shown on my YouTube channel later on, so you can see everything that is happening here. In any case, you also have access to the code. So that's just to give you some ideas as how DarkSide works and how you write malware. So hopefully it wasn't too crazy fast. Well, maybe it was, but I guess it is what it is.
Wow.
Developing malware one-on-one in less than an hour. It's it's crazy.
I think you broke a record, a Guinness record in
Guinness record for sure.
developing malware. So very, very insightful, Pavel, very nice. Guys, thank you all for staying till the end of the workshop. As you can see here, you have a link to the discount we promised. I've also shared in the chat. We promise, so you can enter the workshop, the full workshop in the website and have additional information regarding the workshop and malware development with additional information and broader use cases by Pavel and Uriel. So please insert the code and insert the coupon code and the URL. So guys, if you have any further questions, please write them down in the Q&A. We will now answer several questions in the Q&A, but please feel free to ask. Moreover, I do want to say that all these workshop recordings and presentation will be uploaded to our LinkedIn page. I will share also the link to our LinkedIn page. So several questions from the audience. I can see that Shivam is asking, like when you said API keys or OS keys, can you give us more like that? Maybe it's more for Pavel.
Sorry, I'm not sure I understand the question.
So Shivam's asking, like when you said API keys or OS keys that you can use in your malware, can you give us more like that?
You mean APIs? So yes, usually what you could do is use native APIs that is anti-something like anti-open file, anti-create file, anti-read file, things like that, which are more low level, I would say. So this is also possible to do, although most of them are undocumented. We'll talk about the important ones in the workshop.
Okay. So
you can also make syscalls directly, by the way, which we'll talk about as well.
Okay. So another question by Anonymous, why you did not use the same file handler?
You mean when I encrypted the file? I could have used that. I could do that, but then I would need to use set file pointer to move the file pointer back to the beginning of the file before I write, which means another get proc address kind of call. Not too bad. I just wanted to make it simple to understand.
Okay. Another question by Rain. I hope that I'm pronouncing it well. Can you give the get proc address an alias, like a different name such as of a variable?
An alias to what? A get proc address can only look at exported stuff. It could be exported functions or exported variables, nothing else.
Okay. Another question, would the EAF, the export address table filtering, prevent this find export mechanism, or is iterating over the PEB LDR not covered?
So if you're talking about IAT hooking, then that would not help prevent what I've done here. Because I haven't touched the IAT at all. I'm just looking directly at the exports without going to the IAT.
Okay. Another question, this get module handle, like a function, the get module handler, replacement not get proc address, isn't?
No, get module handler just returns the address where a module begins in memory, just the address of the module, but it's not going to look up any export. So again, I didn't want to use that either, and that's why our function to find an export also returned the base address of the DLL.
Okay. Another question, how complicated detection mechanism like ETWTI, MEM scanners, and kernel callbacks be evaded?
Well, that's a question for a full course.
Sure.
There's lots of stuff there, obviously.
Okay. Okay. So in the full workshop, that's a huge topic. So guys,
yeah, we'll discuss some stuff about the kernel and how kernel callbacks work and what we can do with that. But it's just too much to discuss at this point.
Okay. Another question: are there other alternatives to antiscan.me when it comes to evaluating malware samples for their efficiency? Also, how reliable are the results? Maybe it's for Uriel.
Yeah. So basically, you have more websites, but I don't really know them like thoroughly. I didn't check them, so I will not recommend using other websites other than anti-scan. The reason why is because if you develop a malware, you don't want to upload it to virus totals, so all the EDRs and antivirus vendors will have access to your sample. So the only reliable source that I know for sure is anti-scan.
Okay, okay, that's good.
The code will be shared. I see the question there on GitHub. In fact, I'm going to provide the link right now, but it's going to be available in a few minutes. So it's a good question. Please continue with other questions while I find the link.
Another question is by Manuel. If we want more evasion, could it be convenient to leave some calls in the import that are harmless instead of leaving the import table empty?
Yes, definitely. I would even recommend that because it would make the PE look less suspicious if you have some benign functions. Even read file and write file are like normal functions you might need to use regardless in very common scenarios, and that's a good thing to perhaps leave them there.
Okay. So another question is, how can we detect your dark side malware?
Good question.
A good question. How to detect the dark side ransomware? You need to come to our workshop.
Okay, so you need to be a defender. You need to learn how to become a defender, how to perform more malware analysis in order to
How the malware are developed, so you
yes, how
can
malware
you
are
know how
developed.
to better make.
Remember
detect.
that malware development analysis are the two flips of the same coin.
Yeah.
When you know one, you probably know the other, and you want to know both of them. And that's what we are trying to do in our workshop.
For sure.
Okay, there is a administrative question, Uriel, when the coupon is going to be expired.
Oh, okay. So basically, we're planning to expire it in 1 week.
Okay, guys, be hurry up. I do want to emphasize regarding the question of malware detection. I can add as a CISO that eventually you want to build several protection layers. And of course, you need to have your defenders well known or well understand how to analyze malware, what are the variants or attack vector of a malware, and also build several defense layers. So don't just rely on one or just on your malware analysis team or just on your EDR or any other security mechanism, but rather see it as a holistic attitude and put your own fields and defend layers. So if one layer will be broken, you will have additional layer in order to protect your data. Okay, let's see if there are some last questions. Another by Anonymous. What is the risk of using direct and indirect syscall in process injectant in Maldev?
Sorry, say again?
So the question is, what is the risk of using direct and indirect syscall in process injection in Maldev? Malware development.
Uriel, you want to take that?
Yeah. So what do you mean by risk? Like the risk of getting caught by EDR? If you mean in that way, so again, it really depends on the engine that you're trying to bypass, on the EDR that you're trying to bypass. There are some EDRs that have great hooks and detections on direct and indirect syscalls, and there are other EDRs and antivirus that don't know even how to start dealing with it. So it really depends.
Okay. Okay, so I can see that people are thanking us. Let's see if there are some last question.
I said other like make it longer for 2 weeks maybe for the coupon code. We'll try our best. So you know.
Yes, It's just for the meetup group, guys. So you know, that's for you for your participation. So I can see that there are no further questions, guys. If you have any technical questions, please write down to Uriel and Pavel. Register for the workshop. As you can see, it's very interesting, very insightful. Stay tuned. Please register to our and follow our meetup group on LinkedIn. You have the link in the shared, or scan the code and follow us. The recording of this session and presentation will be uploaded over there. And stay tuned for our next meetup. I do want to thank Uriel and Pavel for a great workshop, very insightful and technical workshop. I'm getting a lot of thanks. So guys, thank you very much. Thank you all for joining. Thank you, Pavel and Uriel,
for having us.
Thank you all.
Bye-bye. Keep safe.
We hope to see you in our workshop.
Of course. Thank you very much, guys. Bye-bye for now.
Bye.
Stay safe.